Hello everyone, my name is Riya Sharma. I am a student at Christ University, Delhi NCR, pursuing BSc in Economics and Mathematics. Today in this video, I will be explaining the topic of properties of a good estimator, particularly focusing on unbiasedness. As we can see, there are four properties of a good estimator, which are unbiasedness, consistency, efficiency, and sufficiency. Here in this video, I'll be focusing on unbiasedness. So statistic T is said to be unbiased estimator of a parameter theta if its expected value is equal to theta. Or we can say in a mathematical term that expectation of T is equal to theta. Now we'll see if sample mean is an unbiased estimator for population mean. So here we can take a sample size of n, and in the sample we have values x1, x2 till xn, and the size of the sample is n from a population whose mean is mu. So we'll take x bar to be the sample mean here, and the formula for x bar is x bar equal to summation of xi, where I is equal to 1 to n divided by n. N is the sample size we have. And we have to prove, as we have already seen, we have to prove that expectation of x bar is equal to mu. That is, expectation of statistic is equal to parameter. So now to prove that, or see if the sample mean is actually a unbiased estimator for parameter, so for population mean, we'll see since xi is drawn from the population whose mean is mu, expectation of xi will also be equal to mu, where values of I can range from I to n. So expectation of x bar will be equal to expectation of summation xi upon n, and here we will expand this to x1 plus x2 plus x3 and so on till xn divided by n. Now since we know the property of expectation, that expectation of ax is equals to a into expectation of x, and we've used the same property here. We've taken out 1 by n and we have the rest of the value as expectation. Now also there is another property that expectation of a plus b is equal to expectation of a plus expectation of b. We've used the same property, and then we have 1 by n expectation of x1 plus expectation of x2 plus so on till expectation of xn. Now since we've seen above here that expectation of xi is equal to mu, so we'll put the value of expectation of x1 or x2 or xn till xn equal to mu. Then we have 1 by n mu plus mu plus mu till n. Now if since it is still n, we can write it as n mu, and when we cancel the n from n, we will be left with mu. Hence we can say that expectation of x bar is equal to mu, and we can say that sample mean is an unbiased estimator for the population mean. Now we'll see if sample proportion is an unbiased estimator for population proportion. We'll take the similar sample size and sample space, which will be x1, x2, xn of size n from a population whose population proportion is p. So we'll take p cap to be the sample proportion like we did here for x bar, and p cap will be equal to summation of xi divided by n, where values of I ranges from I to n. Since xi is from the same population, expectation of xi will be equal to p, where I can be from 1 to n. Now expectation of p cap will be equal to expectation of summation xi upon n. We will expand that to expectation of x1 plus x2 plus so on till xn upon n. Using the same properties, we'll take 1 by n out, and then we will split these terms into expectation of individual terms. And since we have seen here expectation of xi equal to p, we'll put those values. It will be repeated n times, so we can say 1 by n into np, n will be cancelled by the other n, and we'll be left with p, and we can say that expectation of p cap is equal to p. Thus sample proportion is an unbiased estimator for population proportion. Now we'll see the same for variance, and if it is not a unbiased estimator, then we'll find out the unbiased estimator for variance. So we'll see if sample variance is an unbiased estimator for the population variance. Here we'll again take the similar sample size and sample space, which is x1 plus x2, x1 x2 until xn of size n from a population with variance sigma square. Now we'll take S square to be the sample variance, and we'll use the formulas to simplify the value of S square. Since S square is equal to 1 by n summation of xi minus x bar whole square, we'll use the property of a minus b whole square equal to a square plus b square minus 2ab to split this term like this. And then we'll open the summation, which is for the whole, and we'll put summation on individual terms. And using the property, using the formula that x bar equal to summation xi upon n, we can open this summation and write nx bar square instead. Now these two are similar terms. We'll minus this and we'll get summation xi square minus nx bar ka whole square, nx bar square, which will be equal to this n will be cancelled by this n only for this term. So we'll be left with 1 by n summation xi square minus x bar square. Now we have the value for s square. Now we'll calculate the expectation of x square, which is expectation of the sample variance. Now expectation of this term would be, we'll separate this into two individual terms and we'll get these two terms. Here we'll use the formula and take out 1 by n, and we'll be left with 1 by n summation expectation of xi minus expectation of x bar square. Now since we know that variance of a statistic or anything, here we have s, so variance of s is equal to expectation of s square minus expectation of s whole square. So we'll use this formula to derive this formula, which is expectation of s square equal to variance, this will come this side, so plus expectation of s square. Now we have two values for expectation of s square, which is this, and we'll merge these two values to find out a new way to calculate the expectation of s square. So we'll take 1 by n summation variance of xi plus expectation of xi whole square minus variance of x bar plus expectation of x bar whole square. So this and this combined will give this. And since we know the variance of xi is equal to sigma square and expectation of xi equal to mu square, variance of x bar will be sigma square by n, and variance of expectation of x bar would be same mu square. We will take the summation n, then we will have n on both the terms. Since the value of summation is from I equal to 1 to I to n, we'll take this n out, so we'll be left and n will cancel the n. We'll be left with sigma square plus mu minus sigma square by n minus mu square. This mu square will cancel this mu square. We'll be left with sigma square minus sigma square by n, which we will simplify to get this term. Now since we can see that this term, which is sigma square n minus 1 upon n, is not equal to sigma square, we can say that sample variance is not an unbiased, hence it is a biased estimator of population variance. Now since we have the biased estimator, it is easier for us to calculate the unbiased estimator. We can see that only thing that is restricting this sigma square to be equal to this sigma, the other sigma square is 1 n minus 1 upon n. So we'll reciprocate this term and add that with multiply that with s square to get the unbiased estimator. So as you can see here, we have reciprocated this term n upon n minus 1. So this term will cancel out this term further, and we can get the unbiased estimate. So n minus 1 expectation of s square, this has come out, we'll be left with this cancels this, and we have sigma square, which will mean that this is the unbiased estimator for our population variance. And this term, if we take s square equal to this value, we can simplify further to get the unbiased estimator, which will be 1 by n summation xi minus x bar whole square, and we can cancel this n from n, and we'll be left with this value is equal to s square here. Thus we can say that 1 by n minus 1 s square is an unbiased estimator for sigma square. So hence in this video we have learned the concept of unbiased estimator, and we have seen that population that sample mean is an unbiased estimator for population mean. Sample proportion is an unbiased estimator for population proportion, but sample variance is not an unbiased estimator for population variance, and hence we have calculated an unbiased estimator for the population variance. I hope you enjoyed this video and the concepts are clear to you. Thank you so much for watching this video.